Elon Musk has recently published a paper which deals with BMI. He did it in the context of his company, which is called Neuralink. And as the name suggests, this is going to link the brain to the computer. Is he going to succeed in it? And what did he actually write in this paper? Elon Musk, which have brought us with Tesla, the innovative car, and recently also with an innovative truck, is also planning to take us to Mars, and now is also planning on getting inside our brains. Join me to discover what did he write in this paper. This is Programmer's Quickie, where we learn anything from software engineering best practices, cloud computing, the latest JavaScript framework, math and statistics, syntax, programming highlights, and the latest technologies. Join me as we discuss architecture and in this episode, the latest paper from Elon Musk from Neuralink. The Singularity is Near is a book published by Ray Kurzweil, who is currently working at Google. He is also one of the main contributors to OCR, recognition of text, to the synthesizers, and many more computing and physical instruments. Also, the e-ink that you are probably holding and reading books from is also an innovation which Ray Kurzweil has participated in. In the book The Singularity is Near, Ray Kurzweil scans the power of computing and he is correlating it to what computers can do. He has predicted that the singularity that should happen in the next coming like tens of years, up to 100 years, the brain would connect to the computer, and with this we will start a new era where the new human would not be able to understand what was the previous human, or the reverse, the current human would not be able to communicate even. We do not know what is the nature of this new human. As it appears, Elon Musk takes things seriously. He is coming from a programming background. He is treating the physical world as if it's an application. You open a bug, you open a story, you start working on it, you iterate on it until it's working. He has done it with Tesla, he's doing it with SpaceX, and now he's also planning to do this with Neuralink. When you think of Elon Musk, you should think of a super programmer who has moved all his effort into the physical world. And we'll see in this paper that this is exactly the way that Elon Musk is treating those items, as if it's a software that he's iterating upon and building. So if we are looking at a brief overview of this paper, what Elon Musk is trying to do is to take the current world state of BMI, brain-machine interface, which is the communication channel between the brain and the computer, which we achieve with electrodes and wires that we connect to the brain, and he's trying to increase the bandwidth. So what he's claiming in this paper is that up to today, it was pretty difficult to implant wires and have it accurate and be able to iterate on it and have the right computing and the right software. And we did not have enough bandwidth. Just think of an old modem and compare it to today's fiber. Okay, so he is trying to take the current technology and move it to the next level. And the next level is going to be a high bandwidth. Like we are going to listen to the neurons and give the commands, And all this would be streaming, just like you stream through Apache Kafka or other streaming servers. It would be streamed into the main computer, processed offline. You would be able to visualize it just like you visualize your metrics. You would have proper testing and you would have proper robots that would know to accurately implement and implant these wires into the brain. Now let's get to more details about it now that we know the overview. So in his paper, Elon is like waking up in the morning and now trying to build a machine that would implant these electrodes. He describes that he wants in the paper and that he has achieved to be able to implant as many as 3,000 electrodes. So these are like 3,000 mini wires which are connected inside the brain to the neurons, and he then splits them between 96 threads. So the question is, how do you implant them? Do you do this manually? Do you need a surgeon? So his answer in the paper is that his company has built a neurosurgical robot which is capable of inserting 6 threads, a total of 192 electrodes per 1 minute. So this robot is capable of inserting 192 electrodes per minute, and each thread can be individually inserted into the brain with micron precision. So a micron is like 1 millionth of the unit. Let's see what this unit is. So this is a thread that is inserted into the brain, okay? And it's very, very small. Okay, it's like a micron of a meter. And then at the extension point, you need to connect it to some computer. So how does he do this? So as of today, it's not wireless. He's using a USB-C. So yes, just like a USB-C you have on your computer, Elon has on the brain of the mouses that he's testing upon. It's providing him with a full bandwidth of data which is streaming from the device into the computer. So he needs this robot to be able to control the insertion of the wires into the brain with a very high degree of resolution. And this can help in the future with helping with the speech and helping with the motions. As of today, he's using 3K wires. Up to today, the normal or the standard that was tested upon in example was 256 electrodes, which is like divided by 10 by what he has achieved. And this has already, with 256, you can have people control the computer cursor, or you can do speech synthesizer for humans. So just imagine what you can do with 10 times this now count of wires. The main problem that we had so far, at least one of them which he describes in the paper, is the limited bandwidth that we had. So we could not have small enough wires to be able to be more precise in where we insert these wires. Okay, and because we didn't have such small wires, then the insertion of them to the brain was invasive, and he wants a non-invasive approach in order to record millions of neurons through the skull. If you just record all the neurons outside of the skull, then the signal is very distorted and non-specific, and you want to insert the wires. Alas, once you insert the wires, you are doing invasive, and this is risky. So what is done is first to shrink the electrodes into what's called microelectrodes, and then use a robot which is super precise, like on a micron scale. And then what you could do is insert very precisely these little electrodes, as simple as that. These wires are very thin, they are flexible, they are multi-electrode, and they are built from polymer probes. However, because they are so small and thin, then it's very problematic to insert them inside the brain because they are elastic. You try to insert it and it's because of its elasticity, it moves and bundles. So they have taken the robotic approach in order to insert it. In order to achieve all this, he is using very slim electrodes. In fact, he divides it between three major components that allowed him to achieve an increase of scale of magnitude, because he's moved from 250, which is the current standard, into 3000. And the three components of technology that they are building in Neuralink in order to achieve this is first an ultra-fine polymer probes. These are the small electrodes. Second, a neurosurgical robot, which allows you to insert those very slim and very tiny and micro electrodes. And thirdly, a custom high-density electronics. This custom high-density electronics allows you to take all the data, to process it, and to transmit it via the USB-C that is connected to the skull. The thickness of the actual threads which you implant in the brain, and the thread is a collection of wires, a collection of electrodes, so the thread itself, its thickness is between 4 to 6 micrometers. This means 1 millionth of a meter, so 4 to 6 times of this. And it includes also, in this diameter, it includes up to 3 layers of insulation. They are also using a thin film polymers that have previously been used for electrode probes. But their low bending stiffness complicates the insertions. Therefore, they developed the robotic insertion approach. The robot's insertion head is mounted on 10 micrometers, globally accurate 400 millimeters by 400 millimeters by 150 millimeters travel axis. So its travel axis is a few centimeters, and it's called a small and quick swappable assembly, like a needle pincher. In the robot, they have the insertion head that we have just discussed. And it's holding an imaging stack. So not only it's implanting the wires, it also knows to transmit those images. And those images, then you can look at them live on a computer as you would have expected. You have a viewing, and you could do then verification that everything is okay. You could also let the computer process those images with all the machine learning stuff that we have today. And it also have like a flashlight and illumination that excites the fluorescence from the polyimide that is inserted and allows for the optical stack to view it. This is a sub-micron visuality to view the actual operation. He also puts an emphasis in the paper into the actual programming and the hardware that he has on the computing stack. He has an integrated custom software that allow the pre-selection of all the instruction sites, so that it would enable him to plan before the operation exactly where he wants to insert the threads, and then he would click play and the robot would do his job. There is also a surgeon that is monitoring the whole process, and just like in the Tesla car, he can just click the stop button and do some minor tweaks. They should be very careful in the paper he is describing of damage to the blood-brain barrier, because it holds a key role in the brain's inflammatory response to foreign objects. So they don't want to trigger the brain's inflammatory cycle. Everything can be automated, and everything is automated. The surgeon can have full control, and if desired, he can make manual micro adjustments to the process. There is a 300 micrometers spacing between the threads in order to maximize the coverage. So each thread would have its own region. It's like a city that it's controlling. When they implant such a device, there is what is called a chronic recording from thousands of electrodes. It's going to take a lot of time, and they are meaning to leave it there for a lot of time. So they need to have a special package that would hold the pace of time. This recording stack must also be small. It should supply all the electricity, and it should amplify the signals that are coming from the brain, and it should reject out-of-band noise. And it should operate all with low power. They are using ASIC for that, which is composed of 256 individually programmable amplifiers. They call them the analog pixels. They have on the hardware a USB-C connector, as we said, in order to transmit the data. They sample the brain at 19.3 kHz with 10-bit resolution. The whole AC consumes a very low amount of electricity, only 6 milliwatts, including everything. This also allows for easy replacement because all the parts are easily replaceable. This is how they designed it for iteration. This is the programmable part of Elon Musk, where he's taking programming practices and inserting them into the physical world. They are also using FPGA in order to have the actual programmable components. FPGA are the field programmable gate arrays. And in real time, they also monitor the temperature. They have an accelerometer and also a magnetometer sensors. They connected then to a 10 gigabyte Ethernet on the protocol of UDP. They can therefore visualize everything in real time. They also write it to disk in order to persist it. And the neural data just begins streaming automatically when you connect any cable into the brain. To sum up, Neuralink is taking the current BMI and trying to upgrade it to the next level, to actually get some real data from the brain, and in the next steps to be able to also implant signals into the brain. They are doing this with the robotics, with the emphasis on iteration, on being able to replace the parts, not only the software but also the hardware. They are trying to take much minimal wires, much shorter and much slimmer wires. They are composing it into threads, and they have a great vision. They actually try to take what Ray Kurzweil has described that would happen in the future when we connect to the brain to the machine, and they are actually trying to implement it, just like you implement any software like Spring Boot. And they are doing this with an emphasis on iteration, on taking the product. You see this everywhere. You see this in Tesla, where they have really high computing. You see this in SpaceX, where they iterate on missile products. And now you see this in this paper on Neuralink, where they iterate on brain-machine interfaces. I hope you enjoyed this. I think this was a very interesting paper, and let's see what Neuralink and Elon Musk comes with at the future.